Bismillahirrahmanirrahim and Assalamu alaikum, my dear students. I welcome you all to the lecture number 8 of Electric Circuit Analysis 1. Today we are going to study Thevenin's theorem. Like other theorem, this is also a theorem to simplify circuits, electric circuits, just like source transformation, superposition and other theorems. In this theorem, we'll also simplify the given circuit. What we do is we replace a linear circuit. Please recall that a linear circuit is in which the output is directly or through some factor k related to the input. And the replacement is that the given circuit is replaced between the given terminals into a voltage source in series with a resistance. The new voltage source that we get as a result of transformation or minimization is called as Thevenin, and the new resistance as a result of minimization of the circuit is called Thevenin and is represented by RTh. Methodology is that if we have a linear circuits between point A, B, so what we do is we transform into a voltage source in series with the resistance Thevenin between the same terminals A and B. And if in case we are given a certain load for analysis purpose, we simply replace the load and summarize and simplify the circuit. Once the simplification is done, you can put the load back into the circuit. So the main thing in this network in this theorem is that you have to find the value of Thevenin equivalent voltage, which we simplify or represent by Thevenin, and Thevenin equivalent resistance, which is represented by RTh. RTh is very simple. You just have to do what you have to do is you just turn off all the independent sources, and you can say, otherwise you can say you set the independent sources equal to 0. That is, a voltage source will be replaced wherever we have a voltage source. We'll replace it by 0 volt or a short circuit, and wherever we have a current source, we'll replace it with a 0 ampere, and you know that a 0 ampere means no current, and that means open circuit between the terminals A, B. The independents sources are off. Thevenin is the resistance. By looking into, actually you look into the circuit from the terminals, indicated terminals. That is, you look into the arrowhead is directed towards the inside the circuit, and then you find what the RTh, Thevenin or Rin is. Whereas Thevenin is the open circuit. Between these two terminals, you find what is the total net voltage of this network, of this linear circuit. Once we start doing it, I hope you will get it. That is, load is disconnected, and then the terminals A, B, behind this you see that what is the total voltage of this network, and that is what we call VTh, or we also can say as V open circuit, because you open circuit these terminals, and in parallel to this you find what is the total net voltage over here. So no current flows into AB. You said that the terminals as open circuit. Thevenin theorem is very important in analysis of circuit. It is used for simplification. Entire circuit is replaced by a voltage source in series, which is we call Thevenin, in series with a resistance which we call as Thevenin. That is, I have a network. This is a load resistance. A load current is flowing IL through it, and the same linear circuit is transformed into a Thevenin voltage source in series with a resistance Thevenin between the same terminals A, B, and the rest of the circuit, which is on the right side, remains the same. So that was the original circuit, and this is the original circuit, and this circuit is a Thevenin equivalent of this entire circuit. Now if I have to find, for example, current IL, so you know that this is a voltage source which is powering these two resistors. The two resistors are currently in series with each other. So if you have to find the current, what you do is you simply multiply the total, add up the two resistors and divide the total voltage by the sum of these two resistors. I is equal to V over R by Ohm's law. However, if I have to find the voltage across this load, then you know that when resistances are in series, the voltage is divided. So I have to use voltage divider rule, and VL will be the same resistance in numerator divided by sum of all the resistance in the network. We have two resistances, Thevenin and RL, multiplied by the applied voltage, which is Thevenin over here. So to have a better understanding of this topic, I would move on to to practice problem number 4.8. I have left example 4.8 for you. It is solved in the book as well. It is very simple, and to have a more grasp over the topic, I will recommend that kindly please go through it. In case you have any problems, we can discuss them in the question answer session. So in practice problem number 4.8, I have this network and these 2 points A and B, which I have mentioned. What the question is that I have to find current I, which is flowing through the 1 ohm resistance, and I have to use Thevenin theorem. So I am limitized to using only Thevenin theorem, and I have to find the equivalent of all this entire network. In this network, I have a voltage source, a current source, 1, 2, 3 resistors. So I have to simply transform this circuit from this end till this end into a voltage source that will be V Thevenin in series with a resistance that is called R Thevenin. So let's move on to solving this network. First of all, we'll find R Thevenin. R Thevenin is very easy. I have to set off all the independent sources to 0. So I had an independent source over here. This is the voltage source. I set it to 0, and 0 volt means I have to replace it by the short circuit. Then I have a 2 ampere current source which is heading upward. I'll set it to 0, and when you turn off a current source, you replace it with an open circuit. We have been doing this in superposition theorem. So the voltage source is set to 0 by replacing it with a short circuit. The current source is set to 0 by replacing it with an open circuit, and then resultant circuit that I get is this 6 ohm is remains there, this 6 ohm remains there, this 4 ohm remains there. So I have to, between point A and B, I have to find what is the total resistance value. So now simplifying the circuit, I get 6 ohm and 6 ohm. These are in series, so I can simply say that 6 plus 6 is equal to 12 ohm, which is in parallel to the 4 ohm. So now I'll find the R Thevenin between the points A, B, and this 12 ohm is now in parallel to this 4 ohm. I'll use the parallel equivalence formula of resistance, and what I get is R Thevenin. The equivalent of this entire network is 3 ohm. So R Thevenin for the given network is 3 ohm. Now we'll proceed towards finding the Thevenin equivalent voltage, or VTH, for the given circuit. In order to find the VThevenin, what I do is, in the previous lectures, lecture 6 and 7, we have been studying source transformation. Now looking at the circuit, I think that I can solve it more easily if I can transform the sources. So what I do is, I transform this voltage source in series with a resistance into a current source in parallel with the resistance. The resistance value does not change. The same 6 ohm now is in parallel to the source. The source, however, has transformed from voltage to current source. The plus polarity is heading upward. That is why I have the arrowhead direction upward. And the new current value, please recall that it is found by using Ohm's law. I is equal to V over R. The original voltage value was 12 volt divided by the resistance, which is 6 ohm. So 12 by 6 is 2 ampere. So this is how I get the new current value, and this is the resultant circuit. Now what I do is, I can simply add this current value and this current value, and I can have one single current source. And this is what I do. I simply these are the same nodes. This is the same node, this is the same node. So I just rearrange the circuit. 2 ampere, 2 ampere, and this is the 6 ohm shifts towards a little bit right. Now I add these two resistance, these two current values. 2 plus 2 is 4. So I have the 4 ampere current source, and both were heading upward. So that's why the 4 ampere current source is also pointing towards the upward direction, and the 6 ohm is still in parallel to this new 4 ohm voltage source. This is the resultant circuit that I get. Now what I do is, I can again apply source transformation to the resultant circuit. This is a current source in parallel with a resistance. So I can transform it into a voltage source in series with a resistance. So I do is, I simply apply source transformation again, and the new voltage value is by V is equal to IR. I was 4 ampere R is 6 ohm, 4 into 6 is 24. The same 6 ohm which was previously over here in the parallel direction now goes into series, and this is how I get the resultant circuit. Now you can see that this 6 and this 6, its two resistances are in series with each other, so I can simply get a series combination and replace it with a 12 ohm resistance. So now the 24 volt voltage source in is series with this 12 ohm. This 4 ohm remains the same and the rest of the circuit remains the same. So I get the simplified circuit as 24 volt in series with these two. I have to find the voltage between Thevenin between point A B, which is almost the same as voltage across the 4 ohm. Now the voltage across the 4 ohm and Thevenin would be the same, because you know that parallel voltages are same. So now this voltage source is powering two resistance which are in series. So what I do is I use voltage divider rule to find Thevenin. Voltage divider rule states that the same resistance is kept in numerator divided by the sum of all the resistance in the network multiplied by the applied source. We have two resistance 12 and 4. I have to find the voltage across 4 ohm, so that's why it's in the numerator divided by sum of the resistance into the applied source. This is how I get 6 volt. Now you can see that I find the Thevenin equivalent. The Thevenin equivalent is 6 volt is the Thevenin voltage. R Thevenin is 3 ohm, and I have the load resistance which is 1 ohm into right back in the place. So now I have to find I. I is simply the current flowing in the circuit, which is total voltage divided by total resistance. The total voltage is 6 volt. The net resistances are R Thevenin plus R 1 ohm. So R Thevenin was 3 ohm plus 1 ohm. So I get a 6 volt divided by 4 ohm, 1.5 ampere. Please solve this example related to this topic yourself, and it is provided, the solution is also provided in the book. In case you have any problems, please do let me know. We'll discuss it in the online session. I wish you best of luck. Take care. Allah Hafiz.